Welcome to the root locus technique. So today in this lecture we will discuss about how to sketch a root locus. So in the previous lecture we saw that a point on the root locus must satisfy the condition of mod kgs hs equal to 1 and angle kgs hs equal to odd multiple of 180 degree. And we saw the example that when we vary the k, we can calculate the poles and we can plot these poles on the S-plane, and we can see how the poles are moving and we can plot the root locus. However, this process is quite tedious and it involves calculation of poles for each value of k. There are some rules, some points. Using those, we can plot an approximate root locus, and we can refine the root locus to those points where we are more interested, and we can get that the information of tangent response and stability from that root locus. So we will discuss those rules that will help to sketch an approximate root locus, and these rules are very simple, and that will help us to sketch a root locus. So the first rule is that number of branches. How many branches a root locus must have? So in the previous example, we saw that here we have this, and we saw that the poles started at -10 and 0, and we have like this, and here we have like this. So the poles start moving like this when we varied k. So the question is, how many branches a root locus should have? So there is the rule that number of branches equals the number of closed loop poles. So in this problem we saw that we had two poles, closed loop poles, and we see that each pole is leading one branch. So there are two branches of the root locus. So the number of branches of root locus are equal to the number of closed loop poles. So one branch for each closed loop pole. So here we have two branches. So this is the first rule. The second rule is symmetry. So here we can say that root locus is symmetrical about the real axis. So it is symmetrical about the real axis. So this is real axis sigma. So here this is constant, omega is 0. So this axis is real axis, and root locus is symmetrical about this axis. We can see here root locus here is symmetrical. Once it it is leaving this axis, it is leaving symmetrically. Why? Because the poles of closed loop transfer function can be either real or complex. When they are real, they will be on the real axis. When they are complex, they will be complex pairs. So there will be symmetry. If a pole is here, there will be another pole here. So they will be always symmetrical about this real axis. So therefore root locus will always be symmetrical about the real axis. The third point is real axis segment. So third point is real axis segment. So real axis segment means where on the real axis, if there are number of poles, where should be the root locus and where it should not be. So this real axis segment for k greater than 0, of course we are taking k greater than 0. So this root locus exists to the root locus exists to the left of the odd number of left of the odd number of finite open loop poles and or finite open loop 0 of finite open loop poles or zeros. So here we should understand this, that why the root locus, if we can see here the root locus is on the real axis existing here but not here. Why this root locus is moving towards this side, not this side? So therefore the segment is only between these 2 points, not this side or this side. So that rule we are going to discuss, the real axis segment. So we say that the root locus exists to the left of the odd number of finite. So here is point is odd number of finite poles or zeros. Why? So let's take one example here. And let's we have here some poles, zeros. There are some other zeros, complex poles, and so on. Now let's take one point here. Suppose that root locus is here. So if that point is on the root locus, the angle of poles minus angle of zeros minus angle of poles should be equal to odd multiple of 180 degree. So here this is going to make 180 degree. However, the angle that is going to be made by this 0, this is positive and this is negative. So this angle will be cancelled out. Similarly, the effect of these angles will be also cancelled out, because this, if this is positive, this is negative, and the effect of these angles is 0. So we can see that if this point is will be on the root locus, if it is to the left side, because this is the left side of this first pole, one pole on the real axis. Now come to this point. If this point is here, of course the effect of these complex poles and zeros will be cancelled, and effect of this will be 0, but effect of this is 180 degree and another this 180 degree, that is 360 degree. So this is even multiple of 180 degree, and so with the condition that there should be the point is on the root locus, it must satisfy the angle condition with odd multiple of 180 degree. So, it is not satisfied here. Therefore, the root locus cannot be at between these 2 points, because here the angle conditions is not satisfied. Again once it will be here, then again this another 180 degree will add it to be 3 into 180 degree, that is odd multiple of 180 degree. So, root locus will be here in this area and in this area, but not in this area. And we see that because complex poles and zeros are, they nullify the angle effect. So, therefore, only we consider the real odd number of finite open loop poles or zeros. So, we consider only these real axis poles and zeros we can consider. So, therefore, the root locus here is between left of this odd number of pole, that is 1, but not here, because this is left of the even number of poles, that is 2 poles. So, therefore, we understand that real axis segment, on the real axis the root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. Now, the fourth point is starting and ending point. Starting and ending point. Means where the root locus will start and where it will end. So, this point we have to discuss. So, the rule is that the root locus begins at the finite and infinite poles of GSHS and ends at the finite and infinite zeros of GSHS. So, it begins at finite and infinite poles of open loop transfer function GSHS and ends at finite and infinite zeros of GSHS. So, let us see how it is possible that they are starting at the finite and open and infinite poles and ending at. So, let us take the closed loop transfer function. So, let us we have Ts equal to kgs upon 1 plus kgshs. So, this is the closed loop transfer function, and this we can also represent as k times ngs into dhs upon dgs into dhs plus k ngs into nhs. Here we have gs equal to n gs by dgs and hs equal to n hs by dhs. So, we represent these two transfer functions in terms of numerator and denominator. Now, so we evaluate Ts for k tends to 0. that is for small gain, for small gain. Why? Because the root locus starts at small gain and progresses at large gains. So here k tends to 0. So for small gain we can write that Ts is, we can approximate here. So at a small k gain, this quantity will be negligible in compared to this. So we can write k ngs dhs by dgs dhs plus epsilon. So epsilon is some small quantity, because k is small, it is small, and so now here ngs by dgs is gs, this is approximate, and this is hs, because it's a so this is negligible. We see that here we have this is more effective here, and this is negligible. So these are what? These are poles of GSHS. Okay, so poles of GSHS. So that's why we say that the at a small gain we are getting this equivalent transfer function is governed by the poles of GSHS, and therefore at starting the gain is small, so the root locus will start at poles. So it begins at finite and infinite poles of GSHS. Now when k is tending to, k is very high, so when k tends to infinite, let's say high gain, we will get Ts is, we can approximate, we can neglect this part. So we will get k ngs dhs by, this is negligible, plus k ngs and nhs. So we can see here that this part is dominating here, this is negligible, and this ngs nhs are the zeros of the gshs. So here this is the zeros of gshs. So that's why we say that at high gain the root locus ends. So therefore we say that it ends at finite and infinite zeros of GSHS. Now we should try to discuss one more point about finite and infinite poles or zeros. So finite poles and zeros we understand because we can compute them. What about infinite poles and zeros? So we saw the finite poles and zeros that we were able to compute from the numerator equal to 0, we get zeros and we put the denominator part equal to 0. So we get poles, they are finite. Now we should know that there could be infinite poles or zeros possible. So if a function can have infinite poles or zeros, function means a transfer function can have infinite poles or zeros. When the transfer function tends to infinity, when s tends to infinity, then it has a pole at infinity. And when the transfer function approach to 0, when s approach to infinity, then it has a 0 at infinity. So let's take one example, k gs hs equal to k upon s plus 1 s plus 2. So we know that here we have 3 finite poles. So s equal to 0 and s equal to -1 and -2. So we have 3 finite poles. Now let's put s tends to infinity. So when s tends to infinity, we will get k gs hs is approximate k upon s into s, because if s is tending to infinity, we can neglect this 1 and 2 in compared to s. Now each s in the denominator causes this transfer function, open loop transfer function, 0 when s tends to infinity. So when s will tend to infinity, each s value will cause this transfer function to be 0, and therefore transfer function is tending to 0 when s is tending to infinity. Therefore there are a 0 in infinity. So each s will cause 0 to transfer function. So there are 3 s, and these 3 s will cause 0 to this transfer function. So there are 3 zeros at infinity. So there are 3 zeros at infinity. So total number of poles, that is finite plus infinite, equal to total number of zeros, finite plus infinite. So this is the rule. So because in this transfer function we saw that there were 3 finite poles and there was no any finite zeros. So here number of poles finite is 3, and we did not find any infinite pole, because when s was tending to infinite, this transfer function is not tending to infinite. So 3 plus 0 equal to total number of zeros finite. So finite zeros there is no any finite 0, so that is 0 plus infinite, and we are getting 3 infinite zeros, so 3. So 3 equal to 3. So here we are getting that total number of poles finite plus infinite equal to total number of zeros finite plus infinite. So if in any this function there are suppose 1 0 is finite, then there will be 2 poles that will be infinite. So now one more point we will discuss, that is this fifth point, that is behavior at infinity so behavior at infinity. So here the root locus approaches straight lines as asymptotes as the locus approaches infinity. And so at infinity the root locus will approach as asymptotes of a straight line, and the equation of the asymptotes can be found with the real axis intercept, means that is a straight line and it will intersect on the real axis with some at some real axis point and at certain angle. So we can find the intercept. So if this is a point, when suppose this is the root locus is going like this, and so it will follow some line as a asymptote, and that line is going to intersect, suppose this is a root locus going to infinity, and this is a line as asymptote, this is an asymptote straight line. So it is cutting at sigma a with some angle theta a. So this we can find. So sigma a is equal to summation of finite poles minus sigma finite zeros upon number of finite poles minus number of finite zeros. So we can see that when we have to find here only these finite poles and zeros numbers and the values of these finite poles, and theta a equal to 2k plus 1 pi upon n minus m. So this is n and this is m, number of finite poles minus number of finite zero, and here k equal to 0 plus minus 1 plus minus 2 and so on. So if we have some example here, let's take one example. So we see that here there are 1, 2, 3, 4 finite poles. So finite poles at 0, -1, -2 and -4. Because Hs is 1 here, so we kgs Hs is this. So and finite zeros at -3. So we have 4 finite poles and 1 finite zeros. So we have 3, and we know that finite poles plus infinite poles equal to finite zero plus infinite zero. So here are total 4 finite poles. So we have 1 finite zero, means 3 zeros are infinite, at infinite, and therefore because they are infinite, and we know that the root locus will lead towards the zeros because they start at poles and ends at zeros, and 3 zeros are at infinite, so root locus will go to infinite. And so at those infinite, how they will proceed will be told by the asymptotes defined by this formula. So when we want sigma a, so we calculate sigma a. So here sigma finite poles 0 plus 1 is -1, -2, -4 minus finite 0. So minus -3 by here 4 minus 1. So that is 1, 2, 3, 4, 7 and plus 3. So that is minus 4 by 3. And then theta a equal to 2k plus 1, 180 by 3. So that is 2k plus 1 and 60 degree. So that is 60 degree and then 180 degree and 300 degree. So these are the angles. So if we see on the S plane this, so we can represent the poles at 0, -1, -2 and -4, and the 0 is at -3. So we can see that the root locus will exist in this real segment and in this part and this part, because root locus will exist to the odd, left of the odd number of poles are zeros. So here is this 1, left to the 1, left to the 3 and left to this 5. 1, 2, 3, 4, 5. So we see that it will start here, it will start here, because root locus will start at poles, and here this root locus will start and go end to 0, and this root locus will start and go to infinite, because there is 180 degree. So this root locus is going to 180 degree, and other two, they will diverge here to the complex plane and they may lead like this to infinity, and their intercept we are getting at -4 by 3, that is 1.3. So here this straight line will tell at 60 degree and this line at 300 degree. So this -60, that is -60 here. So these asymptotes are going to guide this movement of the root locus at infinity. So today this example we took from the book of Norman S. Nice, Control Systems Engineering. So today we discuss these 5 rules of to sketch the root locus. First is the number of branches. So one branch for each closed loop pole. Then symmetry, root locus is symmetrical about the real axis. Then real axis segment, so root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. Then starting and ending points, the root locus begins at the finite and infinite poles of GSHS and ends at the finite and infinite zeros of GSHS. Then at infinity it will approach towards a straight line asymptotes, and the equation was given with intercept at the real axis, that is sigma a and theta a, and we saw this example. So we will continue some more rules to sketch the root locus in the next lecture, and I thank you for attending this lecture, and we see you in the next lecture.